Hello again. So you came back for more mole ratios? All right. Let's see what we can make happen here. Consider the combustion of ethane. You remember we saw combustion reactions and we saw that they're the same every time, so this really is the only thing they have to say. If you light something on fire like ethane, C2H6, the reaction is always it combines with oxygen and out come carbon dioxide and water, usually as steam. So there we are, and we should probably balance this. 2 carbons, 2 there, 6 hydrogen, need a 3 there. Now that means we have 2 times 2 is 4 oxygen plus another 3 oxygen, grand total of 7. And I'm just going to put a 3.5 here. If you'd rather have 7 over 2, no problem, that'll work. If you'd want to double everything, yeah, you can. You'd end up with, of course, 2, 7, 4, 6. And if you use that, you will get the same answers that I'm about to. But I will stick with this one. Let's keep it simple. They say 2.64 moles of ethane burn. So what species are they talking about here? They are giving us ethane, and they want the amount of water vapor. So if we do this with a proportion, we'd say burning 1 ethane yields 3 waters. And then they ask, what if instead we burn 2.64 moles of ethane, C2H6, how much water would we get from that? If you cross multiply this, you get 3 times 264 divided by 1 is, what, 7.92, if I'm not mistaken? Let me have it in the comments if that turns out to be wrong, and I'll shamefacedly fix it. But I believe that's 7.92 moles of water vapor. Or, if you like doing the inline style, then we'd have 2.64 for ethane. And you'd say, if this is 1 and this is 3, what do you do to 1 to turn it into 3? Easy enough, times it by 3. So 2.64 times 3 gives you 7.92 moles for the water. Not too bad. What next? I assume it'll be a different ratio, so we'll just clear those out. 0.0642 moles of carbon dioxide is produced. So now they're asking about carbon dioxide and oxygen. So let's do some more circling here. Now they want us to jump from carbon dioxide to oxygen. So our ratio is, we have 3.5 oxygens for every 2 carbon dioxides. And they're saying 0.0642 moles of carbon dioxide. Remember, our units have to line up, so when they give us an amount of CO2, it must go on the bottom, lined up with the other carbon dioxide. 0.0642 moles of CO2, and this will be moles of oxygen, and I don't know what that is. So, if we're cross-multiplying, we're doing 3.5 times 0.0642 divided by 2. 0.0642 divided by 2, and from that I get x is 0.11235 moles of oxygen. So, easy enough. Now, I'll do this one the inline method, and I'll tell you right now it's not going to work wonderfully. It's going to be a little bit ugly, so will it work? Yeah. Will you enjoy it? No, you will not. We'd be starting with the carbon dioxide here, 0.0642. And the awkwardness comes from, what do you do to 2 to turn it into 3.5? And if you can see that the answer is to multiply it by 1.75, wonderful, then this is going to go fine for you. The other alternative is you take this number, divide it by 2, just to turn it into 1, and then multiply it by 3.5. Neither of those is very nice, but if you do either one of those things, do 0.0642 and do either of these processes to it, you will end up with the same result, 0.11235. So there are some examples that make the inline method look really good, where it's all whole numbers, and then there are examples like this where it looks kind of rough, and I admit this is one of those. So inline, not always great, but it does work if you're able to see your way to this number. This comes from 3.5 divided by 2 is how you get this multiplier, and that might be more gymnastics than you're comfortable with. If so, good thing we have another method. What have we got here? Consider the formation reaction that produces ammonia from its elements. Okay, well, even if they just said the formation of ammonia, we would have assumed it was from its elements, but nice of them to clear that up. So, we're making NH3. The elements it comes from are N and H, but wait, when you have N, nitrogen by itself, it's diatomic, and ditto for hydrogen. So that's our real formation reaction, not balanced yet. And when we balance it, what happens? 2 nitrogen means we need to double this, but now we have 6 hydrogen, so triple that, and I'll throw in a 1 here just to get it all nice. So there's our balanced reaction, and now we're ready to tackle some questions. If 9.18 moles of nitrogen react, they're starting us off with nitrogen, and they're asking how much hydrogen. So our ratio is 1 to 3. We can say 1 mole of nitrogen reacts with 3 moles of hydrogen. But they're not using 1 and 3, they're using 9.18 of nitrogen. 9.18 moles of nitrogen, and we don't know the hydrogen, we're trying to find it. So if you cross multiply, 9.18 times 3 is 2754, divided by 1, 27.54 moles of hydrogen involved. Or, if you're doing the inline, you'd say, I'm over here with 9.18 moles of nitrogen. The hydrogen is 3 times that much. So 9.18 times 3, same result. Next one. Now they're giving us moles of hydrogen, and they want us to jump to moles of ammonia. Well, ratio is 3 to 2. We use 3 hydrogens for every 2 ammonias we intend to make. And they're telling us, what if we use 3.88 moles of hydrogen? That will give us what amount of NH3? Cross multiply, so multiply the opposite corners. 2 times 388 is 7.96, I think, divided by 3. I don't trust myself to do that in my brain, so 2.58, lots of 6s, would be the amount of ammonia. 2.58, 666666666 moles of NH3. If we were doing this in line, we'd be starting with hydrogen and going to ammonia. You'd have to either multiply by 2/3 or divide by 3. That turns this number into a 1, and then multiply by 2. Either one of those will get you to ammonia, and it should give you the same result. And finally, I assume this will be a different ratio, but let's find out. They start us with moles of ammonia, and we're going back to moles of nitrogen. So our ratio, you could do 2/1 or 1/2. It doesn't matter all that much. I'll do, for no particular reason, I'll write 1 nitrogen for every 2 ammonia. And now they're saying we have 2,048 moles of ammonia. That goes on the bottom because my ammonias have to line up. And upstairs we'll get an unknown amount of nitrogen because our nitrogens have to line up. If you cross multiply that, it's 1 times 2048 divided by 2, which gives 1024 moles of nitrogen. Or if you're doing it in line, you'd say, from this amount of ammonia, what do I do to get to 1? I have to take this amount and cut it in half, or divide it by 2. So 2048 divided by 2, same result. And finally, how bad is this going to be? Double replacement. Okay, so it's ionic compounds. That means we have to do some ion stuff before we can write an equation. What have they given us here? Aluminum bromide. Aluminum and bromine, I'll get the charges in a minute, is reacting with sodium and hydroxide is a polyatomic. The charges, for starters, are these. Aluminum's 3, bromine's -1, sodium's +1, the hydroxide is -1. So, for starters, we will have AlBr3 and NaOH, no numbers required there. And now, if there's a double replacement, the metals or the nonmetals have to switch. So, we'll say the aluminum will trade places with the sodium. And what do we get after that? The aluminum jumps over here to be with the OH, so we're going to have Al with OH, charges in a minute. And the sodium jumps back here, so we're going to have Na with Br. And our charges are aluminum still +3, hydroxide's -1, sodium's +1, bromine's -1. So, an aluminum will bond with 3 hydroxides, and you need brackets to make that work. You have to say Al bracket OH, close bracket 3. And NaBr is nice. The charges already match, so we can simply write a single sodium with a single bromine, and all's good. Okay, so that's the double replacement reaction. We finally have it written out. But what? I hope you said it isn't balanced yet, because we need those coefficients if we're going to do any kind of mole ratio stuff. Pink works. 1 aluminum, 1 aluminum. So far, so good. 3 bromine, only 1 bromine. So we need 3 times as much bromine on the right side. But now that I've done that, I have 3 sodium on the right side and only 1 here, so we'll have to triple this. Now that I've done that, I have 3 OHs on the left side, and oh, that's okay. So I think we have this now. 1 aluminum, check. 3 bromine, 3 times 1, check. 3 sodium, check. And 3 hydroxides, check. So that's all balanced. I'll throw in 1s. And now let's see what they have for questions. From 2.12 moles of aluminum bromide, that's this, blah, 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 sodium bromide. For the moment, all I care about is what ratio do they want. And right now the ratio is 1 aluminum bromide to 3 sodium bromide. 1 Albr3 to 3 Nabr. And they say the actual amounts they're using are 2.12 moles of aluminum bromide. 2.12 moles aluminum bromide. And we don't know how much sodium bromide, so that's our X. If nobody's looking, you cannot write the moles here, and you cannot write the species out every single time. I'm trying to be a good boy and write it all out to remind you that the units line up and to remind you what the units of our answer will be. But obviously, on your scrap paper, as long as your shortcuts don't hurt you, they are fine. So, if we're calculating this, we're doing 3 times 2.12 divided by 1. That should be 636. 6.36 moles sodium bromide. Or if you wrote a 2.12 here, easy enough, you'd say, what do I do to this 1 to turn it into 3? The answer is multiply by 3. The sodium bromide will always be 3 times as much as the aluminum bromide. So 2.12 times 3, same answer. What next? 4 and 5 moles of sodium hydroxide. That's this. How much sodium bromide? This is a nice question. Do you see why? This is lovely because these coefficients match. If you ever have a 1-to-1 ratio or a 2-to-2 or a 3-to-3 ratio, that's the math saying these numbers will always be identical. So if you have 4.55 moles of sodium hydroxide, you will have 4.55 moles of sodium bromide. No calculator needed, no math needed. It's like you're in a room with 455 heads. How many people are in the room? Hopefully 455. Those numbers should be the same always. 4.55 moles of NABR. And finally, sodium bromide and aluminum hydroxide are the chemicals this time. So the chemical species this time, I should say. So they're saying we're making sodium bromide, and they want the amount of aluminum hydroxide. The ratio is 1-to-3 or 3-to-1, depending how you write it. I'll put the 3 on top for no particular reason, just to show that it doesn't matter. If you put the 1 on top, your work will look a little different from mine, but you should end up with the same answer in the end, as long as you're consistent about which one's on top and which one's on the bottom. So 3 NABR to 1 aluminum hydroxide, and then they say we have 4.2 moles of sodium bromide. 4.20 moles NABR. And they ask how much aluminum hydroxide? How many moles? ALOH3. 1 times 4.2 divided by 3 is 1.4 moles of aluminum hydroxide. Or, if you like working up here, you'd say whatever the NABR is, the aluminum hydroxide is 1/3 that much. So take this number and divide it by 3. 4.2 moles of sodium bromide divided by 3. Again, you'll get the 1.4 moles. So that was a lot of examples. I hope by the end that it felt a little tedious, because that means you're getting used to it, and we're going to be doing this constantly in the stoichiometry practice at the end of this unit, and I promise throughout the course we're going to be using these ideas of write out a reaction, balance it, and then use the coefficients to figure out amounts of various species. So the work you're putting in now should pay off pretty handsomely.